Hi everyone. Today we have the third and final lecture of this mini course by Professor Tadashi Takayanagi. Today's lecture is in pseudo-entropy and the Sitter holography. Please go ahead.
Yeah, thank you very much for introduction. And also thank you for coming to this final lecture. So as a final lecture, I'd like to talk about recent progress of this kind of fields, like namely idea of pseudo entropy, which is a generalization of entanglement entropy, which is very useful to understand holography and also can be applicable to holography in Dojita space, not anti-Dojita space. To understand holography or quantum gravity in Dojita space is quite hard, but we need some hint, and pseudo entropy can be one of very important hints. That's what I'd like to talk about. Okay, so let me start. Okay, but let me start with this quantum entanglement. I gave a basic idea of quantum entanglement in my first lecture, but today I'd like to give some more details. So as we know, two parts, subsystem A and B in a total system are quantum mechanically correlated when there is a quantum entanglement. So example is like this Bell state. I explained this Bell state. If spin of A is up or 0, and B spins, for example, down or 1, these two spins are completely opposite. And we also superpose the other opposite state, right? Down and up, down and down. And then this gives a strongest entanglement between correlation between A and B, right? Because we know if we know the spin of A, then immediately we knew the spin of B. So this entanglement actually turns out to be some, in the context of holography, it gives a minimum unit of quantum, a minimum unit of quantum entanglement, but this gives in the context of holography, this gives a minimum unit of space, like namely Planck scale of the universe. And for pure states, we can say that there is a non-zero quantum entanglement if wave function is not direct product of A times B. If this is the direct product, we say there are no entanglement at all, but there is a non-zero entanglement if wave function is not factorized into direct product between A and B. This is true. This is the definition of entanglement in pure state. For mixed state, it's a bit more complicated, so I'm not going to talk about it. The best measure of quantum entanglement for pure state, not mixed state, but for pure state is known to be this entanglement entropy I already explained in past lecture. So and roughly speaking, entanglement entropy is counts number of Bell pairs between this Bell pair between A and B. So today I'd like to I'd like to give more details of this claim. But as we already discussed, the usual definition in at least high energy physics or condensed matter physics, entanglement entropy is defined by minus rho log rho. It's von Neumann entropy. And rho is now it's a reduced density matrix. Right? We decompose Hilbert states into A and B, and we trace out B. And the observer can only see information inside A. So this is and such an observer see this reduced density matrix. This is a probability distribution, right? So we originally start with pure state. It's just a single state. No ambiguity of information, just size just one single state. But after we trace out B, because observer can only see A, region A, so we have some ambiguity. That is a probability distribution. And it's a Shannon entropy of this probability distribution is entanglement. This is a definition of entanglement entropy. This we already talked about before. And in the case of quantum manifold systems, we have many spins, and we can just choose this 9 spin to be A, for example. You can choose any other part as A. And anyway, A and B are factorized. Then you can define entanglement entropy. And in the quantum field theory, we take a continuous limit so that infinitely many spins and the space is infinitely small. Epsilon is the lattice constant. It's a distance between two different spins to different sides. So, and in the end, we get a continuum picture. In quantum field theory, we can just specify boundary way to define entanglement entropy. So this is a quantum field theory, but let's think in quantum entanglement entropy by looking at some quantum information textbook. So then you will see that another definition of entanglement entropy, but these two are completely equivalent. So set up, so again, we have a spin system. We have A spin, B spin, they are interacting in general. And it's just factorize. This first 5 spin we call A, and the other 3 spin we call B. Then HA times HB, right? Direct product. Hilbert space is product. And then we define following 2 operations. So these operations motivated by a real experiment. So you can imagine one laboratory is, so I'm in now in Kyoto in Japan. So I have some one laboratory, and you have in laboratory in your country. So then it's really remote, right? It's very distant. So it's not easy to do some sophisticated operation, like quantum operation. Like if you want to act unitary operation between me and you, it's difficult, right? It's so distant. It's I think even current technique is very difficult. But inside, in my laboratory or your laboratory, it is possible to do a very sophisticated operation, like measurement or unitary transformation, right? Some laboratory, for example, quantum optics usually do this. So that is actually what we are going to use. So each laboratory, A or B, we can do some local operation. This is a very sophisticated quantum operation. Projection measurement or unitary transformation or many other more generalizations are. This is a local operation. We call it local operation. This is quantum operation. But A and B are far apart. So they are entangled actually. So let's assume A and B are entangled, but they are far apart. So we can only send, right, like this Zoom or like emails. We can send some classical information, right? Classical bits. That is a CC, like classical communication. So we can send some information or sending back between A and B. This is a classical communication. This is something like we expect what really we can do. So under this operation, what we can do? This is a question, and we want to define quantum entanglement like this way. Okay, so there is actually maybe one question. How to exactly know that the system can be? System can be, yeah, this is actually in spin system, it's already clear, right? So you can just write down what's the Hilbert space, right? Spin, each spin, if you specify each spin, right, then you know Hilbert space. That's obviously factorized, right? So it's, just in terms of, okay, so maybe like it. So in terms of Hilbert space, it's 0, 0, for example, 1, or like this, right? Let's call this is the number 1, number 2, number 3, right? Then it's 1, 2, 3, right? And so 1, 2, 3. This is obviously defined, right? This is only 2 choices, right? For Hilbert space 1, we can 0 or 1, right? And we can choose the same thing 0 or 1. But in quantum mechanics, we can take a superposition of these 2 states, right? So this is obviously Hilbert space is factorized. But quantum field theory, we have to be careful, right? So it's if we do this kind of discretization, it is okay. But in a continuous distribution, these 2 sides are, next to each other. Really, distance goes to 0. Then it's not, this is a bit subtle issue. So this is more properly, if you are interested, really continuous description. So you have to look at something very complicated algebra called operator algebra or Neumann algebra. That's recently there are many developments, but I try to avoid that kind of complication. And but that if in terms of continuum language, entanglement entropy is not well defined because it gets UV divergent. I explained this area law divergence, right, in my first lecture, and this is divergent in mathematics. Divergent quantity is not well defined. So in that sense, entanglement entropy is not properly well defined in quantum field theory, but always you can define this quantity in a lattice system. So and that is an effective description of that. And this holographic description of ADS-CFT also puts some lattice constant. That's the reason we can define finite quantity on that way. Anyway, so yeah, factorization is very good, actually, very well defined. And another thing, just in our discussion, there is some relationship like antipolar map between A and B. Sorry, what? Actually, I'm not sure that about, I'm not assuming any antipolar mapping. This is a completely independent. A and B are completely independent. So no relation between A and B. But the point is that for pure state, you can have this relation, SA equals B. Because entanglement measures between, right? Correlation between A and B, right? That should be only one quantity can be defined, right? So A and B are correlated to how much, right? That means SA and SB should be same, right? From the viewpoint of A and B, correlation amount of correlation should be same. So anyway, this is entanglement. So, but anyway, we define this local operation and CC and thing, and we define the rel and CC. So by using that, let's just define entanglement. So this is this operation. It's originally quantum system AB is very complicated, right? Very complicated. So for example, you can imagine like this state, this kind of state. But in even 2-qubit system, 0, 0, right? Plus 1, 1. But let's take some constant alpha and beta, right? For example, let's think alpha and beta is generic value, right? Alpha and of course beta has this normalization constraint, but generic. Then we cannot extract, right, bell pairs, right, from here. Bell pair is like square root 2, square root 2, right? It's not easy to. So what in that case, how? So maybe we can say zero entanglement, right? This is because we cannot extract bell pair. This maybe entanglement will be 0, but this is not so useful, right? So I mean, only if this square root 2 is non-zero entanglement, then it's not such a quantity. It's not so good. So to define good quantity, we take an infinitely many copy of that, like this. We take an infinitely many copy of this state, for example. Then, so there are many spins, right? Because there are so many spins appears. So I mean, originally just one spin, but 2 times m, it's like many spins. And then for this very large system, we can act LOCC, right? For A, we take a local operation, but C, between A and B, we can take a classical communication. Then in the end, we can show that we can extract some number of bell pairs. We can change this complicated system, complicated state into just bell pairs, number of these bell pairs, just number of these states, some number. And let's take, we get n bell pairs, maximally n bell pairs from this system by LOCC. Then we take this ratio, right? Because we take already m copy of that, we take n divided by m, right? This is for each one of this state, how many EPR pairs are extracted. This ratio is important. And if we take this ratio, m goes to infinity, m goes to this infinity many, but this also infinity many, and take ratio, and that actually turns out to be entanglement entropy. It's low log rho. This formula is really recovered. So this is actually quantum information theoretical definition. And this is clarify the meaning, right? How many EPR pairs, bell pairs we can extract. This is a very important fact. And I will give some generalization of that for pseudo entropy, and that where you can find some derivation of this claim later. Okay, so let me go on. This is a basic issue of entanglement, but in this talk, this is a nice theory, entanglement theory. This is called also resource theory. And but we want to generalize some entanglement entropy, and that is defined, and it's called pseudo entropy. And one motivation is to generalize entanglement entropy to post-selection procedure. Post-selection, we started some quantum state, and just one state. If we take one state, we measure entanglement. This is entanglement entropy, but we started quantum state and do some final state projection. And that case, how many bell pairs appears in the intermediate state. This is the motivation. Another motivation, we want to just do more general holographic entanglement. Just if we think, as I mentioned in the first talk, so Euclidean time-dependent background, so we can have a very nice minimal surface, minimal area surface. What this area means, this is a version 3 holographic entanglement entropy. This is a formula. This is a motivation 2. And also, we want to generalize holography to Dojita space, not just ADS. And then if we think holographic entanglement for Dojita holography, then naturally we reach idea of pseudo entropy. That I will explain later. Okay, so these are basically motivations. So these are main references in my talk. So this is the first paper which originally introduced this quantity called pseudo entropy. And the second one is a more detailed analysis in terms of Dojita holography. And this one is finally I'm going to talk about. This is some another way to discuss Dojita holography, not using pseudo entropy, but in the end we get some similar nature. This is our latest one. That also I will introduce. Okay. Let me go. These are contents. So I finished the introduction and then go to version 3, holographic entanglement entropy formula. This is motivation. And then introduce main part of this idea of shared entropy and holographic calculation. And then I'm going to talk about application of the shared entropy for quantum phase transition and jitter holography. And finally, I'm going to talk about how to probe jitter space from conformal field theory. Okay. Okay, so let me go back to this holographic entanglement. So this is, I already explained many times. So this is a holographic entanglement entropy for static spacetime. So this is an anti-jitter space. This is a boundary of ADS, right? Boundary of ADS. This is an extra dimension. And the metric, ADS metric looks like this. Metric gets divergent here. So that's the reason we get this area is an entanglement entropy, and this area gets divergent around the UV region. This gives the area row divergence. And this is a formula. So you should take a minimal area surface, minimal area, and so that this gamma A is we compute this area of gamma A, and this gamma A should be homologous to region A. This is a homologous relation, and the boundary of gamma A also should coincide with gamma of A. Sorry, boundary of A. Okay, so this is a holographic entanglement at the whole static space-time. And now we go to time-dependent case, but this is a Lorentzian time-dependent case. Such a case is we call covariant holographic entanglement. So in generic Lorentzian asymptotic ADS space-time is dual to time-dependent quantum states. This is a usual consequence of ADS CFT. So time-dependent. So maybe you can imagine some gravitational wave inside the bulk. And then the idea is to take some time slice as a boundary. So it's just depend on time, right? T equals 0 or T equals -1. And but the situation completely changes. It's time dependent. So let's take T equals 0, for example. Or sorry, T equals T. Then we define quantum state here. And that is a psi T. This is dual CFT state. CFT states here, the psi T, and the bulk is non-trivially time dependent. And we trace out B again, and then we have a time-dependent reduced density matrix. And then we take a low log rho minus low log rho that define time-dependent entanglement entropy. And this time-dependent entanglement entropy is computed as this minimal surface, sorry, extremal surface area, like this. And it's like this surface at T equals 0, for example. Maybe later we go to T equals 1. Then you get another surface. We take a same region. We take this region, this size looks exactly same. This is A, but it's a surface modified. And so its area also modified. So it's dependent on time. And if there is a several candidate, we should take a minimum over that. So this is a covariant prescription. Time dependent. This is a generic Lorentzian asymptotic ADS spacetime is a Lorentzian time dependent. So such a case, real time, this is real time dependence. So that case, we can calculate extremal surface area, and then you can calculate the entanglement entropy. Okay. So now we go to the third formula. That is a Euclidean case, not the Lorentzian. So Euclidean case, we cannot go right-like direction. Right-like direction is just zero area. It's not interesting, just trivial. So we need an extremalization instead of minimum area. But now we are talking about time dependent, but the Euclidean ADS. That case, minimal surface area is well defined and highly non-trivial. Also, that area depends on time. So such an area is well defined geometrically. So what does it mean in CFT? Maybe it's like similar, some sort of quantum information theoretical quantity or some related to entropy. But the answer is not entanglement entropy. You have to generalize the concept of entanglement entropy. That's the reason we consider this new quantity, shared entropy, in our first paper, this topic. So we call this shared entropy. And let me explain what the definition of shared entropy. So this I didn't explain this in the first lecture. So here, let me go in detail. So idea is to, so entanglement entropy is defined for one state. Like you can imagine this, like just one state and trace out B, and this density matrix, reduced density matrix. But now we start with two different quantum states. This is because Euclidean path integral, you have a initial state and final state is different in general. if we have a time-dependent source. So there are two quantum states, psi and bar phi. Right? This is our initial state. You can think this is the initial state. This is the initial state. Initial state, and this is the final state. So this is, and then we combine these two guys, the brand, okay, to like this to define transition matrix. So this is the inner product here, and if psi and bar phi are the same, right? This is the inner product just one. This is the usual density matrix for total system for pure states, right? If these two are same, just psi psi. This is just usual density matrix, but this is now it's asymmetry, and this is not Hermitian. That's actually very important. This is not a Hermitian. But anyway, we can still decompose Hilbert space HA time. This is the same thing. And then we can also define reduced transition matrix just trace angle to be. This part is the same as usual entanglement. But then formally, at least we can define shield entropy by minus trace tau log tau. This is the same form as von Neumann entropy, but difference is tau is no longer density matrix. Tau is not Hermitian. That we have to be careful. So in that sense, this is not guaranteed to be a non-negative quantity. Like it can be complex value actually. And for Rényi version is defined this way. It's just the same as Rényi entropy. Okay, so now let me talk about the basic property of this guy, shield entropy. And in general, this guy is not Hermitian. So this is now two states, it depends on two states, so we write it this way. This transition matrix, psi, initial state is psi, and final state is by phi, right? Like this way. Like this. And so this guy is not, in general, not real value, not a real and non-negative value. So there is a many discussion here, but still there is some nice class where this quantity always takes non-zero and non-negative value. And that case, we have geometrical dual, right, using area safety. Area safety is just area. It's always non-negative. But in general, it can be complex value. That is very important in context of Dojita space holography. So anyway, either psi or bar phi has no entanglement at all. Either of that is a just direct product. Then immediately this quantity turned out to be zero. So that means anyway, this quantity is related to some sort of entanglement. And if we flip this initial state to final state, it's just become complex conjugate. This is, I think, clear from this definition. And the SA equal SB is always true, still true, even though both can be complex value. And if psi and bar phi are the same, this is the Rényi entropy. That's what I mentioned. And this is just usual density matrix, and this is a usual reduced density matrix, just usual entropy. Okay. These are basic property. So one comment is that in quantum theory, what we are doing something like this. If we take some operator expectation value of some analog of that, then we are considering this kind of average. So usually we start with the same state, right? We sandwich by the same state, but now we choose initial state and final state different, and define some operator expectation value this way. And that is, you can realize this in terms of reduced transition matrix language like this. This is an unusual quantity, but this is quite well studied in the context of quantum information theory. This is called weak barrier. And this can be, even though OA is a Hermitian, this barrier can be in general complex barrier. And even though it is complex barrier in explicit operator, you can measure this quantity by experiment, by measuring real part and imaginary part independently. There are many works in that direction. But in the context of our shield entropy can be regarded as a weak value of modular operator, modular Hamiltonian. So it's like this. Shield entropy is given by HA. HA is just defined by log of tau A, transition matrix. And in then, this is related. This is in terms of holographic language, HA times turns out to be area operator. Just compute the minimal area, such as. So in area safety, usual, holographic entanglement entropy, if bar phi and psi are the same, this is well-known fact. Modular Hamiltonian equal to area operator, but this is some generalization of that to student.
Hi, Tadashi. I have a question.
Yes. Sure.
Yeah, sorry, I have a question. So here, I'm a little bit confused about the. So like in general, we say like a TFD state. If you take the high temperature region, then it's basically in some sense corresponds to the BTZ black hole, right? So you can consider you can consider a TFD state and the time evolved the TFD state, which has a post-selection final state, and then you can compute the pseudo entropy for such a setting. So initial state is TFD state, and final state is the time evolved.
That's right.
But I think as that case, it's kind of like the complex volume. But you also mentioned that for holography theory, it generally real valued for the pseudo entropy.
That's right. Yeah, good question. So yeah, particular. So what you are saying, that's actually that is what you mentioned is some field double state and right. You mean TFD, right? TFD.
Yeah, exactly.
And the time evolution, right?
Yeah.
So that case actually turned out to be just summary entropy with some, analytical continuation, actually, IT.
Yeah.
Actually, we are preparing some, we're going to have some paper related to this issue, but anyway, some property of this kind of quantity. So that's a good question in that sense. But what I had in mind for holography, it's different. So this case, you have a like Lorentzian time evolution, right? Like this way.
Yeah.
So this is not I have in mind. So of course you can do. This is also pseudo entropy. This is also part of particular example pseudo entropy. But what I mentioned for real valued, right? This guy is a completely Euclidean path integral. So it's not. I'm not talking about this kind of IT. Instead of that, I'm talking about this kind of tau h, for example.
I see.
So that case is a guarantee of real. So yeah, it's a good question. That is when. So the situation where we have this real valued pseudo entropy is always real valued Euclidean path integral. So we do some path integral to define bar phi and psi. We put some kind of source, right? But the source should be real valued in terms of Euclidean path integral.
Yeah, I see. And another question is like so basically we can also consider the post selection as some final state value, and for final state, so for some for some system which can summarize, so basically your initial state has some quantum information, but for the final state, I think due to the summarization, it will lost most of its information. So can we still see for this quantity to see some effect of summarization?
Summarization, that's a good question. I think should be possible, but that case is more, I think, related to this time evolution. Yeah. This case, you can see this, such a, equilibrium for this case. This guy, actually, this is actually, we're gonna submit during this week. And this is based on the work with Pavel Kapta and the Bowen Chen, and also Takashi Tsuda, who is my student, and me. But this is, this quantity start with usually if it's t equals 0, right? This is start with this data, but this in then decreases, and in then it approaches some summer value.
Actually. Oh, so it's kind of like the spectrum for factor, right?
Right. Something similar behavior happens. It's like very similar. Very similar. That kind of behavior happens. So yeah, I think that's probably related to your question. But it's that case is highly oscillating, like a spectrum of mark. So if you take the average, you get some value.
I see. Okay, thank you.
Good question.
Sorry, a last question is that in this case, did you compute the thermal pseudo entropy or the entanglement pseudo entropy?
Thermal pseudo. This is a particular case, like as you mentioned, like this kind of situation.
Oh, I see. Okay.
This case is very simple, but of course you can generalize the other pseudo entropy, but more difficult to calculate, but it's possible. I expect something similar.
I see. Thank you very much.
Yeah. You're welcome. Okay, so So anyway, I talked about this. Now I go to this. Okay. Quantum information theoretical meaning. This is related to the issue I raised just in the beginning of this talk about this entanglement, this distillation. So this argument. So we extract some number of well pairs, right? This is called distillation, entanglement distillation. But actually, you can the other procedure is called entanglement formation. We start from bell pairs. We create some orbital quantum state, and actually for pure state, these two guys are the same. Actually, if you have n bell pairs, you get the m, and also if you have m, then you can get n bell pairs. This is reversible. It's like an equilibrium situation in terms of resource theory, and that happens for pure states. So that's the reason entanglement entropy is just equal. These two are precisely good quantity. So anyway, we want to do the similar thing for shield entropy. That gives another motivation, but this is not exactly general. We are focusing on particular states. So, but the claim is that, so, I mean, class E is something like a quantum state with these simple states. And the claim is that shield entropy is the number of distributable bell pairs as an intermediate state between these two initial state and the final state. A post-selection procedure, initial state is psi, and buffer is the initial final state. But for this is on this claim is only true for some good class of quantum state given by this. This is something we call class E. So this is the psi state is cosine theta 1 0 0, sine theta 1 0 1 1. This is first spin 0 and the second spin 0, right? 1 1. And the psi 0 0 and 1 1. But it's different angle. So in that sense, obviously different from usual entanglement entropy. And the shield entropy turned out to be this real value. Yeah, this is a transition matrix, and this and this is a plot. Some finding, but some other values like this takes complex value. So I would like to eliminate such a situation. I just focus on this case. This is a plot. So this is if theta 1 equals theta 2, then just usual formula for convolution. So how can we understand this quantity from distillation? This is the question. So we take a psi state is this state, and we take a m copy, right? M copy times m, and we do some binomial expansion like this. And so C1 is the cosine theta 1, S1 is the sine theta 1. You can imagine this binomial coefficient. We take a m minus k multiplication, this k multiplication, such a term. And the point is that, so there are many, if we do that, so for example, maybe let me write it here. Okay, so let's take this, maybe we take 0 0 state to be maybe m minus 1. And 1 1 state, maybe just 1. Then you get like, A state is 0 0, almost 0, but it's finally 0, not 0 1, and the other for B it's 0 0 0, but 1, right? So we combine these two guys, you get this times m, right? Times 1. So A 0 0 means AB, huh? Small AB, but we have an m copy of that, so this is the m qubits here. And then this means that this is A equal this is like, this means that, so C, M combination number, K, I'm talking K equal 1 state. Right? This is a K equal 1 situation. K equal 1, it's like, C1 times M minus K power, right? And S1. So because this time is M minus K, and this is 1, just 1, right? M minus 1, just 1. So CM1, this is just equal to M, right? The C definition of C is here. And that means, so we are considering this kind of set, but this location of 1, right, can be inserted in other places, right? That's the reason degeneracy is M. So we have to sum over each possibilities. But the point is that this summation is turned out to be maximally entangled state, right? If you sum over these, for example, 0 0 0 0 0 0 1 0 0 0 0 0 0 0 1, right? AB, and we sum over next one 0 0 0 1 0, for example, and 0 0 0 0 1 0 AB, and sum over m such terms totally, and that is the maximally entangled state. So point is that this is a very complicated state, quantum state, but we relate in terms of maximally entangled state and some linear combination of maximally entangled state. And coefficient is just given by this. Okay, so I'm just talking about the AK equal 1, right? 1 0 0 or 0 1 and so on. Okay, there is a question. I have another, okay, so, but let me go. I will come back later. I just want to focus on this EPR pair thing. So yeah, anyway, of course, k equals 0 case is just all terms, the m copy of this guy comes, right? M multiplication. So that is C1 times m and just 0, 0, 0, 0 state, right? No 1, 1, right? 0, 0, 0. And we some of many such states. And then we do projection to maximally entangled state. So one of these are linear combination of maximally entangled. We just choose one of maximally entangled state. So this guy or other guy, and just projection, do some projection measurement. This is a local operation. Like we project only for A. We just do local operation for A. We do local operation. Then, so this such operation looks like this, like pi k. Is if we this number is k, like 1, 0, 1, and we pay there is a pk sector, and we want to project down to pk sector. So that's operator is given by pi k, right? Pk sector. And the probability where this projection works, right? It's like pk, right? So it's this is divided by this one. This is probability distribution, basically. So we initial state is psi and final state is bar. And we do inside, we insert this projection operator. So this is a probability distribution. And that gives this one. You just take this ratio. And yeah, so yeah, this inner product. So this inner product is just this one. And this guy is this guy. This is obvious, right, from this coefficient. So we have also, right, bar phi to n's power, m's power, and we do the same, right? Same expansion, but in terms of C2 and S2, only different. And other guys are the same. And we just take over. Okay, so this is a probability distribution where this K, projection K is realized. K state is realized. And then we just compute the number of distributed very pair for each fixed K. So there is a M such as CMN, CMK states appear. Right? There's a maximal entangled state between CMK K states. So log of CMK is an entropy for each maximal entangled state. For maximal entangled state, we just use usual formula log of W, right? Number of microstates. This is number of microstates. That is given by CMK, right? This is CMK. And but we take we have to sum of each K and with some weight given by probability distribution. Right? Of course, sum of PK is 1. Sum of PK is 1. So this average number of Bell pairs which included in this state between psi and buffer. And that turns out to be precisely, we do some saddle point approximation. If you are interested, you can please try this expression. We take M goes to infinity, of course. And in this limit, we do some saddle point approximation, then you can precisely prove this in a very elementary calculation. This S is exactly this one. C1, S1 appeared here. So this is how we understand this claim, right? So shear entropy is the number of distributed Bell pairs between these two different quantum states. And if we set precisely size buffer in other special situation, theta 1 equals theta 2, this is just original derivation of this claim I mentioned here. This one. This is a well-known fact. This is you can look at Nielsen Chuan textbook, for example, but this is these people prove this. And this is so this argument here is a generalization of that. And if we set theta equals theta 2, then precisely reduce to what we know very much. Textbook results. Okay. Okay, so now let me go, but let me come back to some question. There is a question. So I have another question. Can we use real value condition of shear entropy to characterize geometric states and distinguish from other non-geometric states? Yeah, but I mean, for shear entropy always involve two different quantum states. That's the one thing. And of course, even in such a situation, I don't think GHG state appears in a geometrical way. So that sense, yeah, it should be possible. But typically, to say, in order to say holographic state don't have usual classical gravity dual don't have a GHG state, is to lack some inequality, right? Tripartite mutual information, something like this. But unfortunately, for shear entropy, we don't know. Basic inequality, and Also, we don't have a good candidate of this tripartite like thing, so I cannot definitely answer this question in that sense. But I mean, anyway, DHG state and other states can be distinguished, just usual entanglement entropy. I think that's enough for this purpose. Yeah, anyway, to understand, I mean, behavior of this pseudo entanglement entropy, and the, I mean, property of quantum state is still not completely understood. So it's like a developing subject, I think. Anyway, okay. So, but there is other quantity actually known in a. There is other some improved quantity. So improved means because this is not right, real, always real value, right? This is good, as we will see, this is good for holographic purpose, but for maybe some application to non-equilibrium physics and so on, maybe there might be there a good quantity, which is always non-negative and has some clear quantum information meaning. So I may explain quantum information meaning, but this is only true for this kind of special class. So there is actually such a quantity. This is something called SBD entropy, which we recently introduced. And that is defined by this, like this way. So this is absolute value of transition matrix is like just take a tau dagger and tau, not square root. This is such a matrix. This is a matrix, not a value. It's like a matrix and tau log tau. But the good thing of this guy, absolute value of tau, this state is Hermitian, already, obviously Hermitian. So that sense, this is non-negative and bounded by also dimension of Hilbert space. This is no longer true actually for pseudo entropy. And it has a nice, at least formally have a nice quantum information meaning because SVD means singular value decomposition. So we can take a singular value decomposition of this matrix, tau A. This is not Hermitian originally, but you can always do some diagonalization by singular value decomposition. Lambda is the eigenvalue matrix. And then, so this quantity actually defined for this lambda actually is only dependent on lambda basically. So lambda is quite well defined and obviously Hermitian, and that reason this quantity is well defined. And once we admit initial state is like acted by U and final state is acted by B, then you get a nice matrix and we can easily extract EPR pairs. And exactly the same thing what I explained here. This is obviously because this psi and bar is actually essentially same in this case. So that way we can easily extract number of EPR pairs, so we can understand the SVD entropy for any choice of psi and bar. This is true. This claim is true. But however, there is a one problem or some disadvantage, but this quantity is very difficult to calculate in holography. So let me focus on pseudo entropy, and I'm not going to more details of this guy. But basically, especially in the context of quantum many-variable system, pseudo entropy and SVD entropy behaves very similar according to our numerical calculation. Okay, so now I got a holographic picture of pseudo entropy. So very simple formula. So we define pseudo entropy, and this is just equivalent to minimal surface area in time-dependent Euclidean background. And for this path integral, why we need a Euclidean path integral? So there's a path integral, there's a gravitational wave inside, of course, but the Euclidean time. So Euclidean time, and this path integral defined, for example, bar 5 state. But this initial, from past integral defined psi state. That way, these two guys are different. This is the reason why we need two different states to define some some quantity depend on two different states related to this area of gamma, right? This area of gamma. But anyway, so we can easily confirm basic property, like if rho A is pure, then this is 0, because right, if rho A is pure, that means it covers everything, for example. Then it's just trivial. And not if psi and bar is not entangled, there is actually end of. So I mentioned end of the world. I explained end of the world, right? In second lecture, end of the world is just here. If And then this state is not entangled at all. Then because the end of the order, it can end, right? This tip can end here, but if we go this distance goes to 0, then this surface gamma is just vanish. So this is true. And S equals to B obvious, right? B is here. And for B also we use the same surface gamma to calculate the entanglement. Sorry, shouldn't. However, so this is related to previous question, but for example, inequality like strong subjectivity or more other entropy or more complicated inequalities, actually we cannot apply here because it can be easily violated. So because there is a no causality, so in principle you can take this zigzag shape of time slice. Right? You can take this guy and let's call this the A and B and so on, right? And C, and it's a bit funny, but if you do so, then it's easy to find some example where any inequality is violated, strong subjectivity is violated. So the inequality is not still completely understood. And but the derivation of this formula is very easy. So just basically same as Lukowitz-Maldacena derivation of holographic entanglement entropy. So you can do that just replicatory. So from the replicatory is the same, right? Because we have a subsystem A here, and the path integral from above is psi, phi, and this from lower part is like psi. And we can insert two different operators at different locations. Then already these two guys are obviously different. If this operator is in the same place, then these two guys are the same. But so that sense, replica collection doesn't change so much. We just take n copy of NC to calculate this guy, and then we reach this picture. And this is just usual standard replica trick. So that's saying we can apply this to another argument. Not the same way. Anyway, okay. So, okay. So now using the, I'm going to also take a break, maybe after 10 minutes or so. But before that, let me talk about quantum phase transition. So this is one application, first application of this shield entropy. So this is actually condensed matter application. So in condensed matter physics, quantum phase transition is very important, and that's the reason why entanglement entropy was getting so popular in condensed matter theory. So there are so many, maybe thousands of papers where entanglement entropy is computed in quantum spin chain or more complicated quantum models, and the motivation is to detect quantum phase transition. So in other words, it's an order parameter. So the natural question is, should entropy also can be some order parameter? And answer is yes, and it's different from, it looks different from entanglement entropy. It shows some interesting new nature, new property. But first of all, the basic property is just usually the same as n. First part is the same as entanglement, area law. So shield entropy, so if we divide the space into two parts, A and B, and then you can assume there are many spins or quantum field theory also fine. Then this area law is true. It's very easy to confirm. Now I'm talking real part of it. Sorry, I'm talking real part of this. And but the new thing is to take this difference. So we have these are shield entropy. Sorry, this is a mistake. This is 2-1. So this is a compressed conjugate. This part is the same as 2 times real shield entropy. And this part is just average the entanglement. So entanglement is we know already. So and shield entropy is new, right? It's good to compare these two, right? How much shield entropy can be enhanced? This is the delta S. This is a very interesting quantity. And but you can see most of the case, this is always non-positive, negative. If these two guys are in the same quantum phase, this means that, for example, you can think some scalar field theory, and you can define psi1 as a ground state of scalar field theory with some mass m1. And if this is psi2 is a ground state of scalar field with different mass, then this actually this plot, right? This is a psi m2 minus m1. This difference is just this difference. This is delta S is always negative, and when m equal m1, of course, it should be 0, right? It's two states the same, and this is a von Neumann entropy, this is von Neumann, this is also von Neumann. Then everything is a entanglement entropy, gets cancelled. 1 and 2 is equivalent. But otherwise, it's like always parabola, like it's like negative. So in that sense, I mean, because they are same phase, right? We just change the mass, but essentially same phase. So the question is that can we have this kind of situation? It can be, is delta S can be positive? So this is the question. But answer is yes, and this appears in the interesting case when these two states, psi1 and psi2 are in a different quantum phase. You can take this Ising model with transverse magnetic field, right? This is a well-known model. And if J, let's take H equal 1, right? We set H equal 1, this is just 1. Then J is smaller than 1 because this term is large, so it's a paramagnetic phase. And if J is positive, larger than 1, then this term, ferromagnetic interaction is very strong, so we get a ferromagnetic phase. And there is a phase transition between just J and there is a phase transition point J equal 1, right? This is a paramagnetic phase, this is a ferromagnetic, okay? And we take psi1 and psi2 in opposite way. Then actually we can realize like this is this delta S, right? This delta S, so delta S is just different. This is a average entanglement entropy. This is a pseudo entropy. So pseudo entropy larger, right? So this region is really delta S is positive. And this only happens because we take J1 equal 1/2, right? So J1 is like here. But J2, psi2 is now it's like more than 1, right? This is a 1. This is a 1, so it's more than 1. So it's psi2 is situated with the other quantum phase. Then it is possible that this guy can take a larger value. Okay. It can take I mean larger than 1. It's larger than. Sorry, it can be positive. Delta S can be positive. So that sense, I mean, we find delta S positive when psi1 and psi2 are in a different quantum phases. So that way, you can imagine, you can think this pseudo entropy as some quantum order parameter, detect two different quantum phases. Okay, and one more comment is like this heuristic interpretation. And after that, I think we have a break. So heuristic interpretation. So I mean, another application of entanglement to condensed matter physics is some topological phases. Right? If we have a topological phase, then we cannot use correlation function, or there are no idea to define correlation length, right? Because all correlations become trivial. In topological phase, everything gapped. But nevertheless, if we calculate something called entanglement, topological entanglement entropy, is just part of entanglement entropy, then you can detect as a finite contribution, area of contribution not important, but a finite constant contribution, we can distinguish different topological phases. And what about pseudo entropy? So this is a Euclidean, let's take this again Euclidean time. And then this first path and future path integral gives one quantum state psi1, and past path integral gives psi2. But there is a interface here at this point, and we take subsystem A to be here, right? And then we calculate. So you can imagine that, for example, this is a paramagnetic field, this is a ferromagnetic field, like this previous example, but maybe more radical, you can choose this one topological phase and second different topological field. Then you get some kind of gapless mode around here. But even this example, right, this border is a quantum critical point, a lot of degree of freedom here. So, and anyway, we take subsystem A to be here, exactly on top of interface. So then if we calculate entanglement, this should be enhanced, right? Because only here is a gapless mode appears. And there is this in the bulk is completely gapped, no degree of freedom. Only massless mode localized here. So entanglement entropy is increases. From the viewpoint of ADS safety, so it's a completely gapped, so ADS space, but it's like a cap off, right? ADS space time is very small. So like this, ADS, but it's capped off. This is a Z direction. But in a critical point, it goes to like this, right? This becomes an infrared, right? So UV. So infrared region is capped out in a gapped phase, but it's a gapless phase. It's like opens up. Infrared, this slot is opens up. And that only happens here. That happened here. it's rarely ADS appears. So minimal surface area gets large. But here it's only like very small. So minimal surface looks like this. It's very small part. So that way, entanglement entropy, shield entropy enhances only at this critical point. Right? So that way we can find this kind of. We can also expect the same result.
I'm sorry.
Yes?
I'm sorry. How do you know
Mm.
this gapless interface has a gravity too?
Gapless phase is CFT, conformal field theory. So it's dual to ADS, using ADS safety.
But that's only when
Mm.
that's only when the conformal field theory is the central charge goes to infinity.
Okay, you're right. Okay. I'm talking about a very heuristic picture. You're right. So in general, we don't know. I mean, whether ADS safety is true for generic conformal field theory. That's right. That's right. But I'm talking about. But we expect that even, for example, order central charge equal 1 CFT have some very quantum gravity quantum duality. That's I mean speculation. But anyway, you can, if you like, you can just focus on the large central charge theory here. So this is a large central charge topological theory. Here, then you can see that. Yeah, okay.
Okay.
Anyway, but without using ADS safety, you can imagine this, right? Because this point is really gapless mode appears in whole generic situation. So entropy should be enhanced. Compared to the massive quantum field theory and massless conformal field theory, obviously massless conformal field theory has a much larger entanglement. So that's basically what I'm saying basically right there. Okay. Good. Okay, so this is I wanted to talk. So next session I'm talk about Dojita holography. So it's like context slightly gets changes. So let me have some break here. But if you have any question, please ask. Please unmute and ask question now. Okay. Okay, so let me continue. But by the way, I send the slide to you, so to chat. So if you are interested, please use that. Okay, so now I'd like to talk about Dojita holography, but it turns out this shield entropy, which I discussed today, is also useful to understand that holography. So this holographic entanglement entropy suggests that this extra dimension, spatial direction in ADS CFT correspondence emerges from quantum entanglement. However, this universe, the universe we live currently, and has been considered as a Dojita space, like positive cosmology constant, and rather than anti-Dojita space, negative cosmology constant. So of course we want to understand more realistic universe, namely Dojita universe. So, but then question is that if this claim is true, so namely does our universe emerge from Dojita space emerges from quantum information? This is still not completely understood. So to understand better about this point, let us consider holographic entanglement in Dojita gravity. But anyway, before that, let me give a brief summary of what we know about Dojita holography. So this is a sketch of DSCFT, Dojita space conformal field theory duality, first proposed by Strominger and developed by Witte and Maldacena, and until now. But I should say, there are many different versions of holographic Dojita space, and this is the most oldest one, and most authentic one, I should say. And but recently there are other ideas, but I'm not going to talk about other ideas. Let me focus on this original DSCFT correspondence. So the claim is just very simple. It's a holographic principle, so bulk to boundary correspondence. Dojita space looks like this metric, right? dt square and cos t is exponentially growing, right? Size of universe exponentially growing. And it is also always useful to go to Euclidean signature to define quantum state, right? As we also use many times. This is a Hartle-Hawking prescription. And for Dojita space, Euclidean signature, we just get a sphere, right? And we have a semi-sphere and continue, Lorentzian continue to time real-time evolution. And the boundary of this space-time, boundary of Dojita space at the future infinity, actually, t equal infinity, then we have a sphere, right? T equals infinity, we get this sphere. This is a boundary. So if we holographic principle is true and we can just naturally generalize, then bulk gravity should be equivalent to some theory on the boundary, future infinity. But future infinity is Euclidean space, right? So that should be Euclidean conformal field theory because it lives on a sphere, d-dimensional sphere. And bulk is d plus one dimensional Lorentzian Dojita space-time. But this is very unusual if we know much about ADS-CFT because we have time directions extra dimension, right? Time shift dynamically emerges from Euclidean signature, Euclidean CFT. This is actually really even difficult to imagine, right? How time emerges. So space direction emerges, right, in ADS-CFT, but this is much easier to understand in terms of length scale or length scale in renormalization group law or real space renormalization group law, which is also realized by tensor network like picture. But what about time direction? How time direction emerges? That's the whole point of DS-CFT. Okay. And but anyway, the claim of DS-CFT, so some quantity should be equal to some quantity. Like ADS-CFT, partition functions are equivalent, but this partition function in gravitational spacetime is a path integral up to this point. This is a Euler-Dwight wave function. This wave function universe equal to CFT partition function here. This is a relation. This is a claim of DS-CFT. Okay. Now, but what we expect for DS-CFT? So let's assume DS, I'm talking about already inside DS is Einstein gravity, classical gravity dual is Einstein gravity, and what we expect, right? So D plus one dimensional Dojita space is this metric, and we can go to Euclidean signature by this kind of weak rotation. Euclideanization, yeah. And then we also, interestingly, you can change this L is a DS radius. You can change, go to imaginary radius, and also define law in terms of I theta, then you get the ADS metric, anti-Dojita metric. So in other words, anti-Dojita space and anti-Dojita space and Dojita space are related by changing radius into I times radius, imaginary radius. So imaginary radius Dojita space is actually ADS space. And imaginary radius of ADS space is Dojita space, right? Like that kind of connection. And the central, then we are looking at degree of freedom, and degree of freedom is related to, described by something called central charge. I talk about two-dimensional conformal field theory, then D equal 2, right? The L over Gn is a central charge. But because radius becomes imaginary, so this is a definition of central charge in ADS-CFT, but in terms of DS-CFT, it becomes I times D minus 1. These are dimension, space dimension. And D equal 2 for two-dimensional conformal field theory, ADS-3 CFT2 or DS-3 CFT2, D equal 2. So I, imaginary value appears. So central charge becomes imaginary for D even, including D equal 2 case. This is a very shocking fact. But we have to think such an unusual theory. This already says that dual theory is non-unitary, not the usual value, so it's a non-unitary theory. And the central charge gets also larger when classical gravity limits, that means Newton constant goes to 0, C goes to very large, right? This is a natural thing. So if, classical gravity, if size is very, very large, so degree of freedom also should be very, very large. And for quantum situation, C equal 1, for example, it should be related to quantum universe, like order Planck scale universe. Anyway, so this is something we learn if we trust this DS-CFT. But one may wonder, is this really sensible? Maybe this is not correct. Maybe some problem happens. But at least we can go further and we can find this. I'm not going to details of this, but if you want to please look at this paper. This is one of our latest development in these few years. We can find an explicit model which gives this imaginary central charge. That is actually given by SU2K, level K versus minimum. This is something well-known, right? Well-known model even in many textbooks of conformal field theory. But we take a large C limit. We need to, and we take unusual choice of level. So originally, this model is supposed to be integrable and only finite number of conformal blocks. But I'm talking about difference. It's a different continuation. non-rational version of SU2 Western model. And then level is taken to be this value. So it's an unusual value, but -2 because the central charge of SU2 Western model like this, take this one. And we want to discuss I to the infinity. So we need to take -2 plus I epsilon. And epsilon is like Newton constant divided by ds radius. And then you can realize what we want here, what we want precisely. And the energy also becomes imaginary. But is this really sensible? Indeed, we can calculate partition function of the CFT, and that precisely produces digital entropy. Like this is a well-known formula of digital entropy. Even if you put some excitation, so E is the energy of excitation, you can reproduce digital entropy precisely, and you can match many other things. And also, I will talk about the entanglement data for this identification. So anyway, here we encounter very, very non-unitary CFT, and that is essentially equivalent to also, you can realize this in terms of Liouville CFT, also recently discussed in another context of double-scaled SYK, but the same model can emerge actually.
I have a question here.
Yes.
Do you know this? You take this level as imaginary. What's the physical meaning of this level K? Can be usually the real number in the user with the Witten model. But now you take it analytically continued to be a -2 plus.
Good question. Yeah.
What's the physical meaning of this? Does the theory still make sense when the K takes such a strange?
At least we can calculate many things by taking this limit. That is true. And at the same time, another comment, this anyway defined analytical continuation of a well-known model. But in terms of, there are two comments. One, you can also, this SU2 measurement, the essential part is given by something called Liouville CFT. And then, I mean, this parameter can be analytical continuous. So we don't, it's continuous. K is all, problem is that here, SU2 measurement model in integrable representation, K is integer and also positive. K should be 1, 2, 3. So why this value is allowed, right? But I'm talking about non-rational extension, and that is equivalent to Liouville theory. And then parameter is continuous. You can change a parameter continuously. And you can just take analytical continuation of all formula. So this is one comment. This is anyway possible. Another comment is that, so by using this duality called found by Gabardier and Gopakma, this funny level actually mapped to another level, which is K is very large, I times very large. I times infinity.
Okay.
I times. But this is also still, you might think I is something funny, right? But this is, you can rewrite in terms of Chern-Simon theory. And this is something famous work by Witten. This is just the Chern-Simon gravity for digital space. And if we want to write down, I mean, Einstein gravity of digital space, you can rewrite in terms of Chern-Simon gravity. And that exactly same as level is I infinity. So that way, many things are connected. Okay. That's basic comment. Okay. Good question. And then, but I go back to entropy, entanglement. But anyway, idea is to just generalize holographic entanglement in ADCFT to DSCFT, what we can get. Here, the sketch, right? So this is the digital space. And this is a dual CFT lives here, right? Euclidean CFT, but lives here. So let's take entanglement entropy. So we take a subsystem A here. And do, for example, the twist operator is here, and we can do replicatory to define entanglement entropy. And how can we compute it in the holographically? So that actually, there is a no point that there is a no space-like geodesic which connects these 2 points, because digital space is really rapidly, exponentially, rapidly growing. There is a no space-like geodesic. And only if we calculate geodesic distance, for example, it's go first in the bulk, in the time-like geodesic, and connected by this Hartle-Hawking, like Euclidean path integral part, and then coming back. So if we do so, length looks like this complex value, right? So IT, this term is I times time, right? It's obviously imaginary value, and this part is the real value, a real value. This guys come from this vector guy. And if sum up this and normalize properly, then it looks like entanglement entropy looks like holographically calculated I times C is a real number. C is just this guy, this ratio basically. This part is the C, CDA. and without multiplying I. This is a real value, but times I, right? But this is some familiar formula. This is usual formula, logarithmic formula for entanglement entropy, but with also some finite constant. So this comes from half of the diameter of semisphere, so like half of the entropy. So, but interestingly, same result is you can recover from conformal field theory by assuming this mapping. Exactly, you get the same result because central charge is imaginary, right here, as you mentioned. Actual central charge is this total thing. I times CDS. It's like imaginary. And there is some, depending on cutoff, so you get this one. So that way, we can recover this result from CFT side. And that means this picture should be correct, right? This holographic picture should be correct. But at the same time, we have to be maybe be careful. So because anyway, here I mentioned that this 2D CFT is the usual formula, but IC and epsilon tilde turn to be imaginary value. So then we precisely get this one. This is a usual CFT result, right? And it's precisely matched. But we have to worry that this entanglement entropy now complex value. So this is not actually not entanglement entropy. This is but more properly regarded as a pseudo entropy. That's the main claim here. So why should entropy appear? So this is the next point. Why should entropy appear? Okay, so there is a 2 is a dual Coxeter number. Yeah, yes, that's right. That's right. If we have SU3, so you get a 3. Yeah. Okay. Yeah. Okay. So this rho A is not Hamish. Why this is true? So you can imagine, right? Anyway, dual theory lives on S2, right? I'm talking about DS3. So I'm talking about sorry. DS3. I'm talking about DS3. So DS3 is dual to 2D CFT on S2, right? But this CFT is funny CFT, very funny, imaginary central charge. But anyway, so we take a subsystem A to be here, right? And we put some ground Keto state, right? Usually these two states are same, right? The same path integral. But this is not the same because in terms of action, so CFT partition function is given by I times the central charge. This is a Liouville theory description. This is a Liouville something called Liouville theory. And because central charge is always overall factor, but I is multiplied because central charge is imaginary. So even though Euclidean path integral, but there is I is hidden, right? This is unusual. That's the reason this state and this state are different. More precisely, what we can say is that if we take, Bura state, right? You can take dagger to define Bura state, psi dagger, but this is different from this. This state, maybe I should write this way. Psi to star. This state and this state are different. This is a usual dagger, right? But we don't here. So if we do path integral I times something, right? But this means I minus I times something, right? Because we take it. But this is always same path integral. So it's like this is defined by I times something, I times action. So this is a minus I, but I is different. So that way, it's a pseudo entropy. Just the initial state and final state is different. So this is a reason why we believe this quantity is pseudo entropy. It should be pseudo entropy. And another thing is very important question that like we asked, right? This question. So our universe emerges from quantum information. So this may especially time emergent time direction. So how we get the emergent time? Is it related to any quantum information? But here, at least partial answer, it's related to pseudo entropy, right? Because you get really time coordinate, time evolution, this guy, is really pseudo entropy because it's complex value, it's imaginary value. So emergent time coordinates seem to be related to imaginary part of pseudo entropy. So real part of pseudo entropy is more related to space-like, emergent to space direction. This is also true for entanglement, usual ADS-CFT. Then pseudo entropy just becomes usual entanglement entropy that's related to space-like coordinate. But imaginary time coordinates seem to be related to imaginary. Real time coordinates seem to be related to imaginary part of pseudo entropy. So this is something we learn here. Okay.
Hi, Tadashi. I have
Yes,
another
yes.
question.
Yeah, sure.
Yeah. So as you mentioned that here, the imaginary part of the pseudo entropy is kind of like the emergent time. So how about the case like previously you mentioned for TFD state? So after the analytic continuation, we have
Good question. But yeah, okay, good question. But yeah, more or less, I think that's true. But I cannot say that so much clearly compared with this one. So it's not so simple interpretation like this. But I think basically that is correct. Yes.
Oh, I see.
Something Lorentzian means complex value of pseudo entropy. That is true.
I see. So at that case, do you mean that since we do the minimization in the Euclidean signature, so is that because the different minimization procedures due to the different shape of the art, kind of like the RT surface, so plays the reason?
Yeah, but anyway, we are talking extremalization here.
Yeah, oh, it's also, yeah.
Yeah, extremalization also here. Yeah, because everything is geodesic, and at this joining point also we can extremalize this joining point.
Yeah.
That works.
I see. Okay, thank you.
Good. Okay, so these are okay. Any more question? I'm going to slightly different topic, but it's essentially related to DSCFT. Okay, so now let me go to final topic. But in the end, this, at the first sight, it's different approach to understand DSCFT, but in the end, we see some similarity of these results. This somehow no Hermitian situation appeared also here. Okay, so this is this is a very honest way, without using any entanglement entropy or any entropy, more honest way to understand DS, holographic dual of DS from CFT. So here, assumption is very simple. We don't talk about, DS space is dual to somewhere. I'm not talking about, we just talk about DS space. Actually, I'm focusing on DS3 again. But DS3 is somehow equivalent to 2D CFT. But we don't talk about where this 2D CFT lives and so on. We are not talking, just talk about some CFT2 because symmetry agree, right? This has a SO2 symmetry, 1-3 symmetry. And this symmetry also appears some Euclidean signature, Euclidean CFT. So very symmetry argument. But even that, actually, we can get some hint how DSCFT is so different from ADSCFT. The previous example also showed holographic pseudo entropy in DS means that it's so different from usual ADSCFT. So we get the same thing basically. So anyway, idea is to put some observer into the CFT. How does the observer feel that he or she lives in ADS? This is something often asked when we talk about the ADS-CFT, often experimentalists ask. So you say ADS gravity is equivalent to two-dimensional some conformal field theory, but how really they can feel? Yeah, how we can test against the experiment, right? For example, we have some very large degree of freedom. So we have some conformal field theory with large degree of freedom or strongly coupled. So is it really ADS space? How really experimentally see this ADS space time? It looks like we are living in D dimension. We don't have a D+1 dimension, right? So to see that, anyway, we need to go back how we really observe many things. So we want to put some observer. So for example, how we can know about dimension we are living in. So for example, we are living in 3+1 dimension. How we know this dimension? So idea is to put some observer, maybe ourselves, right? We have some ourselves, right? We can move, right? We can walk in some direction, and we can only walk in 3 different dimensions, right? X and Y and Z. Time evolution is not more non-trivial, but we can just feel some time. So that way, and as an observer in quantum field theory, we want to put some operator, localized operator at some point. And then we can act some translation to move to other direction, or this direction, or some other direction. And then we also have a time evolution like this. Right? This is something we want to see. And once we know, right, and maybe you might think this direction and this direction, we can formally define 2 different directions, but actually quantum, if these two quantum states are exactly same, this is a fake dimension, right? This dimension is exactly same actually. So that way we can classify how many really independent direction we have, right? So that's the thing I want to do. This very, very honest thing. So how we feel dimension. Okay, so in flat space-time, we can write this. Let's take always two dimension. I'm talking of two-dimension shift. So let's take two-dimension. Quantum field series giving two-dimension T and X, and we can have a Hamiltonian time evolution and a translation P, right? Momentum operator translation, and we can generate different states depending on T and X, right? In general. So this means that we can move some local operator to other location. Okay. But from here, how we can understand third direction, right? So where is the emergent direction, extra dimension? So let's think, but let's start from the ADS CFT, that's something we know very much. So this is the ADS metric, this is a global ADS metric, okay? Global ADS. And this is ADS, and inside is the ADS, and the boundary is CFT. Right? We put some CFT operator or delta. Delta is a conformal dimension. And in terms of bulk fields, bulk fields, some scalar field, M is a bulk scalar field mass. There is a famous correspondence between bulk and boundary. But anyway, so in ADS3, I'm talking about ADS3, then there is a geometrical symmetry, SO2, 2. That is equivalent to SL2R and SL2R. And this is a Virasoro algebra, right? But I'm not talking about higher Virasoro, only L0, L plus minus 1 in this talk. And the tilde means right only. That's left moving and right only. L0 tilde and plus minus 1 tilde. And they satisfy this, because we are talking 0, 1, 2 as a 0 plus minus 1, so there are no central extension. It's just this SL2R algebra. And among 6 generators, how we get to 3 dimensions? So among 6 generators, 3 linear combination trivially acts on this bulk state. So bulk state means we have an ADS space and we excite only one point inside ADS3. So such a state can be constructed from CFT Hilbert space. This is just this state looks like ADS3, but actually this is a hidden. This is just a quantum state in CFT, two-dimensional quantum field state. This is we can explicitly realize. I will explain more. I will give some explicit construction of this. But for this state, even though there are 6 generators, but only 3 linear combination acts non-trivially, and 3 actually other 3 acts trivially. So that's the reason you have only 3 parameters. So you act this 3 to change this location, but other 3 acts annihilate this state. So that's the reason we get the 3 dimension in this code algebra. But you can explicitly find. So this is actually equivalent to something well-known formulation called HKL formalism. But I prefer to do it in a state language, CFT state language. Then answer is given by this. This is a previous long earlier paper. But it's explicitly you can write this. Maybe it looks complicated, but actually this is a very natural thing to do. So alpha is something like Ishibashi state. This has, or maybe this has satisfied this condition, and this is also called boundary states or Cardi states. So it's a kind of delta is a primary state, and it's sum over many descendants. L minus 1, L minus some special state which satisfy this guy. And you can this is we act also pi over 2 time translation. L0 plus L0 tilde is a Hamiltonian. So. And then this state looks like cross-cap state. And anyway, but the point is that there is a 3 dependent. This is obvious, right? This is already 3, right? So this we already know, like H and P, right? L0, L0 tilde is Hamiltonian, and minus is a momentum operator. But new thing, extra dimension appears because we can construct this guy. This low dependence. Low dependence because not only L0, but also we have L minus 1 plus minus L minus 1, L1, because algebra was L2R. By using that, you can really translate in low direction. And because so of course we can have a higher Illustrator, but they are not so important because they are not the symmetry of CFT vacuum. That changes the state, so I mean not so interesting. But anyway, this state is turned out to be conformal field theory state, which is dual to excitation at some point in ADS3 space. If we excite one point, and it depends rho T5, because this is a global ADS3 metric, rho T5, then that's you can explicitly realize as a quantum states in a two-dimensional conformal field theory. So this is our ADS case, and we can calculate two-point function. For example, this two overlap inner product of this set. Then we have one state and one other state. And this indeed you can reproduce well-known green function in ADS3. Delta is a conformal dimension, and that means mass of dual scalar field. So we have a scalar field in the ADS3 that is given by this relation. Delta is a conformal dimension operator. Name is the mass. Any question?
Sorry, this D is the geodesic distance.
Okay, yeah, right. D is the geodesic distance between these 2 points in ADS. Yeah, right.
Thank you.
Okay. So yeah, anyway, this is a well-known formula in ADS3. I mean, just even before ADS3, ADS-CFT. But we can recover by expressly using this quantum states. And also maybe let me mention some quantum information theoretical understanding. This is I'm not talking about entanglement, but this is some information method for Brest distance. This is a measure distance between two different quantum states. It's like given by this, right? It's if this inner product is the same one, then it's the same state, and then distance is 0, right? ds square. But we have this quantum state depend on some parameter, so infinitesimally shifted, like the dx. Dx is 0. This is just 0. Right? So, but this is all we can say. There are no linear terms. It's like always quadratic. And this GAB is called information metric. But in this example, nicely, this GAB is equivalent, proportional to ADS3 metric. So this coincides with ADS3 metric. But we need some kind of smearing, right? This is local operator is very singular. So we act some local operation, but not really point like, but with some small width delta. Then you can calculate this green function, and you get metric also depend on delta. And if delta is a 1 over c, roughly, that's something we expect. C is the central charge. Then this is exactly c square, and that's exactly the same as ADS3 metric. This is a very heuristic argument. But anyway, it's quite natural that distinguishability to different point, right, is related to metric, information metric. So we can do, what we want to do is to repeat this analysis to ADS3 case. DS3 case, Doritta space case. So this is a kind. But here you see some non-trivial thing. It's not so simple. Anyway, if we naively do the same thing for DS, this doesn't work. We need some trick. So this is our latest work. And yeah, we have an ADS metric. And DS metric is like this. I'm talking about something called static patch metric. But you can generalize this to, global metric, which I mentioned before. But you can just coordinate transformation. But it is simpler because these two are obviously related, right? So rho equal I theta, and T is I tau. And as mentioned, ADS radius, it becomes imaginary times DS. In other words, R square ADS is minus R square in DS. Then they are related. And anyway, so ADS case, you can geometrically confirm, you can construct L0 and L plus minus as a killing vector of this metric. You can write down explicit vector in this coordinate system, and you can confirm dagger operation. Complex conjugate L0 dagger is L0, and L plus minus 1 dagger is L minus 1 plus. This is a quite usual complex conjugation in conformal field theory. So we can confirm some standard results. This is usually in the CFT textbook, you get this conjugation. But in terms of DS language, you can again rely to this L0 and L plus minus 1, like this symmetry. So this guy also have a, DS space also have a this symmetry, Virasoro symmetry. But if we write down especially the killing vector and do complex conjugation, just complex conjugation means I goes to minus I, and derivative goes to minus derivative because of partial integration. Right? Del t becomes minus del t, like that. Then we get unusual complex conjugation. L0 dagger becomes minus and also tilde, left moving, right going to right moving. And L0 L plus minus 1 dagger is L tilde and plus minus. And crucial point is this one, this minus sign. So this flip energy. So Hamiltonian is originally L0 plus L0 bar, right? Hamiltonian. So anyway, even in this case also we think this is a useful Hamiltonian, L0 plus L0 tilde. But this guy, if we take dagger, right, because of this minus sign, we get this one. It's anti-Hermitian. Hamiltonian is not Hermitian. So this is a crucial point here. And we get a non-unitary. So even though it looks like Euclidean CFT, symmetry is really Euclidean CFT, but it's Hamiltonian is not Hermitian. So that actually means that even though even if you have a Euclidean time, right, we get something like this, tau h. In Euclidean signature, right, time evolution is given by this, right? But actually this is becomes anti-Hermitian, so that it looks like I times more fundamental Hamiltonian. So it already looks like Lorentzian evolution. Right? Even though we start with Euclidean CFT, but already we see some Lorentzian nature. So that is actually another way to see this emergent Lorentzian time, and also related to shield entropy. Shield entropy is right, time direction natural appears, and we get the imaginary value. So this is a very crucial, and let's see how this works. So now, to probe DS geometry from the dual CFT, again, we put some local operator in the bulk DS, and we want to see some dual quantum state. It looks like this. So anyway, we can construct one candidate of dual state, so tilde. This actually you can find from ADS, analytical continuation from ADS state, this state, you know this state, and go using this continuation, and you can reach this state. Again, Chibashi state and cross cap state, and the time evolution, and the phi direction. And indeed, this guy is anti-unitary, anti-Hermitian, no Hermitian. So it looks like this T, it looks like, sorry, this is tau actually. Sorry, this is tau, I think. But tau looks like Lorentzian time, because this guy is not Hermitian, no Hermitian. So anyway, so we get also the phi and the theta direction. Theta is sort of extra dimension. So you can especially construct this state just following ADS CFT calculation. And this delta plus is a conformal dimension, but in DS CFT case, it's 1 plus minus. So I also appears here. This is conformal dimension becomes complex value in DS CFT. M is a scalar field in the bulk CFT and bulk DS. But however, this is just naive analytical continuation, weak rotation from ADS case. But it's not so good. It really have a problem because the inner product, if we take a dual state, it's just 0, right? This doesn't reproduce any green function in Dojita space. So we need some trick, right? The reason why this happens because dual operation, dagger is unusual. So actually, correct answer we can find is by requiring CPT invariance. So this state already we talked about it, and we need some CPT conjugate, and this involves antipodal map in DSCFT. CPT map, and then the sum of two contributions. Then if you take an overlap, it's precisely reproduce a well-known green function in Dojita space in a Euclidean vacuum. This is a well-known form. And after regularization, also we can do the same thing like this to compute Brest metric. We can calculate, you can produce this information metric which is proportional to logit method. Okay. So this is anyway. So this is a trick, and this CPT conjugation is recently also discussed in the context of global symmetry, global symmetry violation. So in quantum gravity, we expect that global symmetry is eventually broken, and CPT. What about CPT? Right? But if so that CPT should be there, then that means we should gauge it. So, and whole compact space, compact universe, ADS case is not trivial because there is a boundary, but DS case is compact universe, then CPT also should be gauged because global symmetry, it should be violated. So, and if we CPT is gauged, then this naturally appears. This should appear. This itself is not allowed to exist. So we always need to gauge counterpart. It should be active. Okay, so also consistent with that picture. This is this gauging CPT include quantum gravity was proposed by Harrow and Masawa last year, and this, our result also consistent with that. Okay, okay, so a bit early, but I basically finished my talk, and let me summarize conclusion. So in this final lecture, I wanted to argue that the pseudo entropy PE is a generalization of entanglement entropy and can be useful for the following purposes. But anyway, pseudo entropy is dependent on both initial and final states, and in general, it's complex value. And pseudo entropy for non-exotic state is something called class E, some special class. It's like measures the amount of this syllable quantum entanglement in the intermediate states. And delta S for two different states can be positive if they are in different quantum phases. But in the same phases, even though state is different, delta S is always non-positive. Can be negative, usually negative. In that sense, delta S can be new quantum order parameter. And also in ASFT, pseudo entropy is just minimal surface area in Euclidean time-dependent asymptotically ADS background. And this suggests that emergent space-time from emergent space direction from real part of pseudo entropy when there is a Euclidean time dependence. If there is a no Euclidean time dependence, it's just a space can emerge from entanglement, quantum entanglement entropy. But in the case of DSCFT, pseudo entropy becomes inevitably a complex value. In that case, we find that the emergence of time, which is very crucial in DSCFT, actually comes from imaginary part of pseudo entropy. So this is, reflects this non-Hermitian nature of dual CFT. So there are several future directions. Of course, we should ask still what's the quantum information meaning of complex value, especially imaginary part of pseudo entropy. And they can, so further application to condensed matter physics and quantum mechanics, and also implication to quantum gravity. And I also mentioned something called SVD metric. It's holographic calculation looks complicated. It's not so easy, but maybe it is better to understand this connection to holography. And finally, so maybe we can get, so if we find some non-trivial inequality for PE, pseudo entropy, maybe we can get some interesting constraint. Maybe if we assume just a Euclidean real valued path integral, maybe pseudo entropy is always real value, maybe we can find some non-trivial constraint. This is also question related to question asked. But anyway, yeah, these are future direction, and thank you very much for listening to my talk, also all of my lectures. Thank you very much.